Hi, Chris Kuzmal here. Today we're going to talk about rotations of binary search trees. We're going to motivate it by talking about tree rebalancing. We're going to give you a formal definition and then provide some examples and work to develop some intuition and hopefully describe a little bit about why we do use the word rotation. Um, In this example search tree, it takes 4 steps to go from node 0 to node 4. You have to go down right children 4 times to get to node 4. Can have the same content for our search tree, but if the root node is node 2, then getting down to node 4 only takes 2 steps, and indeed it takes fewer than 3 steps to get to any node. So this is desirable to go from this to this in terms of efficiency of accessing nodes. So our tool is going to be rotation to accomplish this. The formal definition of rotation, in this case, right rotation for a node named X, is to take the left child of X and replace that with the right child of X's left child, and to replace the right child of X's left child with X. That's the formal definition. I think for a lot of people that sequence of wordings is pretty confusing. So I think it helps to visually see what is going on. But in order to understand and motivate it, we'll get to a visualization in a moment, but let's motivate rotation a little bit more. And if we spread our tree out, and here's a general tree, if I take this vertical line, then if I move it to the right, I will always go to the successor next in the tree, regardless of a parent-child relationship. So from 5 to 6, I go to the right. From 6 to 8, I go to the right. 8 to 9, I go to the right. 9 to 10, I go to the right. We, by the way, could have our tree or structured differently, but we can structure our tree. We can always spread it out so that now going from 10 to 11, I go to the right. 11 to 13 to the right. 14 to the right. 15 to the right. 90 to the right. We keep moving to the right. We keep increasing to the next node that belongs. If our tree is structured visually this way, then we can simply raise or lower nodes in order to get to in order to restructure it. Or of course we can move nodes around. In this case, we move node 6 to replace node 8, and node 9 gets squished down between 8, 9, and 10. And so we're preserving our vertical line test here and restructuring our tree in a way that actually unbalances it. But if we go the other direction from here to here, we've rebalanced our tree. And we're allowed to do these restructurings as long as we preserve that vertical line test. And notice how we push node 5 up above node 11. That also is allowed as long as we shift it from pointing down to node 6 instead to down to node 11. And we shift node 11, which it is intended to be pointing to node 5 here. Now it's pointing to node 6. Okay, so in general, rotation is just raising or lowering a node. We take that left child, we raise it up, we rearrange the pointers, and that's our rotation. That's all there really is to it. We also relabel the nodes so that what was the left child of X becomes the parent of X. And similarly for the other nodes, we relabeled them to be appropriately. So all tree rotation does is change the altitude of a node, adjusting the parent-child relationships, and preserving higher means you're an ancestor. The notion of rotation comes from thinking of the root as being central. The whole thing seems to rotate. So here we got to include some right movement of some of the nodes in order to give you a sense of rotation. I hope you see the rotation there. And we can, and going one direction is right rotation, and go in the other direction is left rotation. And that's rotation.